Right, on we go. So we're going to do question 13a now. Question 13 was very easy, and you should be getting this. Unfortunately, some people weren't. You have to recognise that there's 6 electrons in this half equation and 2 electrons in this half equations. Iodide, ions, or oxide doesn't really matter. It's the right way around anyway. You've got to, when you write balanced equations, ionic equations have no electrons in. It's really important. That comes up again and again in this paper. People drawing balanced equations with electrons, and you've got to combine them and then cancel the electrons. So you end up with BrO3 minus. Sorry, when I say balance and combine the electrons, you can recognise that there's 6 electrons on this side and 2 here. So to get 6 electrons on the right, you multiply that side by 3. So it should be a bit clearer. 6 iodide ions, which is 3 times 2 I minus. And where are we? Br minus. Sorry, I didn't give you much room to squeeze it in, but most of you managed that. The change in free energy for the reaction is 514 kilojoules per mole. Kilojoules per mole. We've got to be just a little bit careful here that we use everything in joules per mole. So we have to convert initially to minus. So delta G is equal to minus 514,000 joules. And the equation we're going to use, delta G equals minus NFE, when it's been asked to work out the value for E0. I personally would be inclined to rearrange at this point. If you prefer, you can plug the numbers in and rearrange afterwards. Don't really mind. But how many electrons are transferred in this process? Well, we've just worked out it's 6 electrons. And so delta, let's rearrange. So E standard is equal to minus N times Faraday's constant divided by delta G. Plug it in. That's horrible. I can't believe I've just done that. It's late. E standard is equal to delta G minus delta G over NF is equal to 5 minus 514,000 divided by the number of electrons transferred, which was 6, times Faraday's constant, which is 9.65 times 10 to the 4. And that comes to 0.888 volts. That's the answer there. Let's get a bit of focusing going on. Very nice. Now we're going to calculate the standard electropotential for that. So if you look up the values in the data book and you use this equation, so E standard is equal to the the E cell, if you like, or for the reaction is E cell for the E standard for the reduction, take away E standard for the oxidation, just like it is in every other time. And you guys were remembering that better than me in class. And let's think about this. So okay, a little pause there while I was looking up the values for the reduction potentials, right? So the reduction potential for iodine going to iodide is here, which is plus 0.54. Okay, so plus 0.54. So, and that, if we go back to our equation, is iodide going to iodine, so that's the oxidation bit. Okay, so we've been given the value for, we've worked out anyway the value for E standard, which is 0.888, or for the E cell for that reaction. We've just looked up this one, so it's minus 0.54. The value was plus 0.54, but look, it's take away there, and so we need to find out E standard for the reduction, which is the bromate to bromide. So just gets to rearranging now. So E standard for the reduction is equal to 0.888 add 0.54, and that will come to 1.43 when you plug it all in and round it up, whatever. Okay, there we go, done. And as I told you, it's good practice to have to show the signs here as it is in enthalpy changes. I'm going to pause that video and I'm going to do question 14 in a bit.